We have an example problem here. Unpolarized light of intensity 80 watts per meter squared passes through 4 Polaroid sheets whose polarizing angles are rotated 30 degrees from each other so that the last sheet is aligned at 90 degrees to the first. What is the intensity of the light emerging from the 4th sheet? So these Polaroid sheets are polarizing filters. We have 2 equations for polarization. I transmitted is half of I naught. Excuse me. And this is when we start with unpolarized light. The other equation I transmitted is I naught times cosine squared of theta. This is for when we start with polarized light. So in this particular problem, we're starting with unpolarized light. That means we have a bunch of waves whose components can potentially be in any direction. We have 4 of these sheets. It doesn't tell us how the original sheet is oriented. It just tells us that their angles, meaning their filter axes, the angles between their filter axes are 30 degrees apart. So I'm going to draw 4 sheets. If the first one was horizontal, I'm just choosing horizontal. I could choose vertical. I could choose anything I wanted. What matters is that the next axis is 30 degrees from horizontal. 30 degrees from however I oriented the first one. The next one would be 30 degrees from the previous one, which is going to make this 60 degrees from horizontal. And as mentioned in the problem, such that this last axis is 90 degrees from the first. Okay. Since we are starting with unpolarized light, this has an intensity of 80 watts per meter squared, according to the problem. As this unpolarized light goes through filter 1, the light that is transmitted, the light that comes through, is polarized, and it is oriented the same as the filter's axis. I'm going to call this intensity 1 because it has passed through filter 1. I1, because we started with unpolarized light, I1 is just half of that original intensity. That's the general rule for having unpolarized light shining on a filter. Okay. Well, this light is oriented horizontally because we're starting with polarized light. The light that will make it through is aligned with the axis of the filter. This is polarized as well. But to calculate this, we need to use our second equation. I'm going to write it this way though. In our equation up here, I naught means the intensity of the polarized light shining on the filter. So when I'm looking at this I2, it was I1 that was incident on this filter. I1 is the polarized light that will be passing through this second filter. And that's why I need I1 in the equation and not the original 80. So to find the intensity of the light after it comes through this second filter, we need to know the intensity of the light and then the angle between how the light was polarized and the filter axis is 30 degrees. So I2, if I plug that in, so cosine of 30, square that times 40, gives us 30 watts per meter squared. So we've gone from 80 down to 40 watts per meter squared. We're now at 30 watts per meter squared. This light is shining on this next filter. Let me get a different color. Let's go with orange, I guess. The light that makes it through, because there's not a 90-degree angle, some light will make it through. This is going to be our I3. What we want, though, is the angle between the light and the filter. So theta in here is 30 degrees. The light is polarized with this axis. So the angle between this axis and this new axis is 30 degrees. So I3, because I2 was polarized, we need to use this second equation for the transmitted light again. We need the initial light shining on the filter, so that's I2, times the cosine squared of the angle between those two filter axes. So I2 is 30 watts per meter squared. The angle between these two is 30 degrees. So I3 22.5 watts per meter squared. So that's the intensity of this light now, 22.5 watts per meter squared. We now need to take the light through the last filter. Some of the components are vertical. This is our I4. We're going to finally end up with polarized light. In the case of how I chose to draw the axes, this light finally is polarized vertically. The intensity of the light, we just use that this second equation again. We need the intensity of the light as it shines on this filter times the cosine squared of the angle. But that's the angle between how this light is polarized, the one that's shining on this fourth filter, and then the axis of the filter. That's going to be 30 degrees again. If we read the problem, each filter axis was rotated 30 degrees from each other. And so that's why the angle has been 30 degrees for I2, 3, and 4. So the intensity of the light shining on filter 4, 22.5, and then cosine squared of our 30 degrees, I4 is we have roughly 2 sig figs, so 17. I'm rounding that. We've got 16.875. So we end up with approximately 17 watts per meter squared that makes it through. Now, having 4 filters is not necessarily a practical thing. I mean, unless for some reason you need light polarized in a certain way and this is the only way to get it. This type of problem is more just a practice using the equations.